this idea of decoupling into a block arbor triangular structure gives us a useful decomposition of a matrix related to the eigenvalues. So let's suppose we have an eigenvector of A, and we'll normalize the eigenvector so it's a unit vector. Because remember, keep in mind is any multiple of an eigenvector is also an eigenvector. So we can use whatever normalization is convenient. So this is the one we use here. And let's suppose, based on discussion of QR factorization, I form a householder matrix P such that P times X is equal to the first standard basis vector. Okay. Now, remember, P is its own inverse, because that's a property of a householder reflection. So I can just move P to the other side, and it doesn't change. So PE1 is also equal to X, so it goes both ways. If I look at P inverse AP, but P is symmetric and orthogonal, so P inverse is P. Oh, actually, I want to multiply all of this by E1. So I want to form a matrix P inverse AP, which has the same eigenvalues as A, but I want to only look at the first column. So that's the same as PAPE1. Now PE1 is equal to X. But X is an eigenvector of A. So I get lambda PX, but P times X is equal to E1. So as a result, the first column of P inverse AP is just the eigenvalue and all zeros. So, in fact, so if I look at the whole matrix, P inverse AP is lambda, all zeros, and then I have some vector B transpose up here. It fills the rest of the first row. And then I have some other matrix that I'll just call capital B. That's everything else in the matrix. So what I've done is if I can find one eigenvector, I can get a block upper triangular structure and separate lambda from the rest of the eigenvalues of A. So the spectrum of A, I can conclude, is lambda union spectrum of B. So it gives me a way of getting one eigenvalue out of the way so I can focus on the rest. So this process of getting one eigenvalue out of the way is called deflation. Now, keep in mind that eigenvalues are polynomial roots. The same term, deflation, is also used when you're computing polynomial roots and say you find one root, x equals a. You divide that polynomial by x minus a, so you factor it out. That is also called deflation for similar reasons. Okay. So what I can do now is do the same thing to B. If I can find an eigenvector of B and keep deflating, I get this decomposition that I have Q transpose, actually I'll use a Hermitian transpose here, AQ is equal to a matrix T that is upper triangular. And Q is a product of householder reflections, which I'll informally abbreviate as householders. So all the household transformations that were used in these n deflations were really n minus 1. So this, if I rearrange this, I have A is equal to Q T Q Hermitian transpose. where T is upper triangular and Q is an orthogonal or unitary matrix. And this decomposition is called the Schur decomposition. So this is the goal of our eigenvalue finding algorithms that I'm going to develop over the next several lectures, to actually obtain the Schur decomposition of a matrix A. So that decomposition gives us the eigenvalues because they're just the, so the essential point here is that the spectrum of A, which is just the spectrum of T, but that is just the diagonal entries of T. So capital T, this is our eigenvalue revealing form. So we keep applying similarity transformations using orthogonal matrices to A until we reduce it to this upper triangular form. We have a Schur decomposition, we have the eigenvalues. Now, unfortunately, we do not get the eigenvectors unless A happens to be what's called a normal matrix, in which case T, the upper triangular matrix T is actually diagonal. So if we get a diagonal matrix in here, then the columns of Q are also the eigenvectors. So we are going to spend time on the symmetric eigenvalue problem, which gives a diagonal T. And there we get eigenvalues and eigenvectors. But for the unsymmetric problem, getting eigenvectors is much harder, and unfortunately we don't have time this semester to get into that.
So, for A has to be special for us to get any information from Q. Like we're not going to get anything from Q unless A is normal.
Okay. Well, let me go ahead and write this down. Well, okay. I wouldn't say that you get nothing. What you do get are invariant subspaces. And from those invariant subspaces, you can work on them. There are algorithms to work on those to get eigenvectors. So a quick bit of, ooh, this is going to fall if I'm not careful. All right, so A is normal if A commutes with its own Hermitian transpose, or just plain transpose in the case where A is real. In that case, A has this is still a Schur decomposition. So D is diagonal in this case. And that means that the columns of Q are equal to the eigenvectors of A, and the eigenvectors turn out to be orthogonal, so that's a nice bonus. So if a matrix is symmetric, skew symmetric, those are two special classes, but the larger class of normal matrices has this property. Okay. Now, if A is, so for general A, normal or not, the first J columns of Q for any J span an invariant subspace. So for instance, in the simplest case, the first column of Q is an eigenvector. The first two columns, they span a two-dimensional invariant subspace, so knowing that one of them is an eigenvector, you can take a linear combination of Q1 and Q2 to get a second eigenvector and go from there. All right. Now, another comment I can make about general A, and this is proven in the notes. I won't go due to time, I won't go through the entire proof here. Okay, so everything below this line applies to a general n by n matrix A. We can say that eigenvectors that correspond to distinct eigenvalues are linearly independent. Okay. And you can show this first for a case of two eigenvalues and eigenvectors. If one's a multiple of the other, but they correspond to different eigenvalues, so you get a contradiction. And then you can generalize that to the case of k eigenvectors for distinct eigenvalues. Okay. Let's suppose then, suppose the matrix has n distinct eigenvalues. Well then, all of the eigenvectors have to be linearly independent. They're going to form a basis for your vector space. So what do we have then? It turns out we get a different and highly desirable decomposition of A. Hopefully this marker will last until class is over.